Okay, I hope you enjoyed that video on Mr. Mobley and pads there. Um, why is it to jump higher? Because he's added more mass. Potential energy, more mass means it requires much more energy to be able to jump. This energy comes from the work is equal to force times distance. The force that's required to get him up in the air becomes greater. So how much energy is used to move a 200-pound person up 50 inches? P equals mg. Well, you got to do the conversion of 200 pounds. Basically, you take 200 divided by 0.22. Let's see. 1 divided by 2.2. Oh, I had a real screwy thing there. Yep. So it's about 0.45. 0.454 is what we say is a conversion from pounds to here on Earth. Because remember, pounds is a force. But anyway, so 91 kilograms, 9.8 meters per second times 1.27 meters, which would be about 50 inches, takes a lot of energy. So if you added just another 20 pounds there, it becomes pretty intense. How much power is generated? Okay, power in the previous jump. How much power was generated? You remember power? Let's go back and look at it. Oh, there it is. All right, and this is what I'm going to have you do in next week in lesson 9 is your lab is you're going to calculate your power. You're going to time yourself running up or have someone time you, or you can time someone else if you don't want to do it yourself. Like some of you might be, working adults and just like, I'm not running up some stairs, but my kids will. And so anyway, so power, remember, is equal to the amount of work divided by the amount of time. All right, which is and is also equal to force times velocity too. We can do that too. But anyway, so is the amount of work. So let's see how quickly he did it. So we're calculating seems like a reasonable number. His pushing off the ground about 0.1 seconds. I think it's a little bit less than that. But anyway, he's still when he pushes off 11,000. When you divide 1,133 joules by zero point 0.1 seconds, you get 11,000 kilowatts. That's like 113 watt light bulbs burning for that short amount of time there. All right, so now let's talk about the conservation of energy. Okay? Conservation of energy says this, and this is kind of confusing a little bit. But basically, it means the energy before, as long as there's no additional work done, like there's no propulsion system or anything like that done in a system, the total energy remains the same. So the amount of work done before, so the amount of energy before equals the amount of energy after. What ramification does that have? Let me show you real quickly before I go into. So let's just look at the diver. Let's look at a diver because we're going to look at Professor Splash here in a minute, and I have about 4 or 5 questions, and I kind of go off the deep end. What was this? 11,300 joules divided by 0.1. That came out to be 11,300 watts, which is 11.3 kilowatts. Now that's like 1,100 watt light bulbs. That's pretty impressive. Anyway, energy before is equal to the energy after. All right, so let's say we've got that diver. Remember the diver that we had? Let's say he goes up, so that he climbs up the thing, and when he gets up to that initial height, we're saying, okay, he's at his maximum potential energy. That's where we're putting him. He hasn't jumped off yet. He hasn't fallen off yet. Okay, so we go, all right, that's his initial height. Then he jumps, bang, he comes and smacks the water. He's got a velocity when he hits the water. Aha, remember that kinetic energy? So all this potential energy is now converted into kinetic energy. So that's his final velocity. All right. So if we look at, this is the fancy way to do it. If we look at the entire thing, mv naught squared, where v naught is equal to, so let me write some cheaters here, where h initial is equal to 10 meters. H final is equal to 0 meters. V final, we don't know. That's what we're trying to figure out. We're trying to find out how fast he was. All right, so we'll put 1/2, and we do this is equal to 1/2 mv final. I hope, all of a sudden I started to sound condescending. I hope I don't. I don't mean to be. Well, all of a sudden I was just like, man, you sound like a dick. Anyway, all right, so 1/2 mv naught squared plus mgh naught is equal to 1/2 mv final squared plus mgh final. All right, let's put in our zeros. 1/2 m times 0. Bye, Felicia. We don't need that one. Plus mg times initial height, 10 meters. So we're going to keep that one. Is equal to 1/2 mv final squared. We know he's got a final speed, but when he hits the bottom, mgh final is equal to 0. So we can say bye Felicia to that one too. And we wind up with mg times 10 is equal to 1/2 mv final squared. So I really don't need to know the mass of something, because look, I can divide the mass on both sides. So I get g times 10 is equal to 1/2 v final squared. Multiply both sides by 2. See, if I multiply this side by 2 and this side by 2 like this, bang, bang. Oh, not bang there. This stays. 2g times 10 is equal to v final squared. Got to take square root of both sides. Remember that? Ooh, some of you are going, man, square roots. You didn't tell me, dog, I had to do square roots. Yep, sorry. All right, but it's easy. This formula shows up all the time in this class. I like it because we do it all because no matter how high something is, now you can calculate its velocity when it hits the ground. Ballpark, it's an estimate because there's wind resistance as we saw in the dropping of the basketball. Okay, let's stop here.